Baby. Aloha, welcome to Wednesday. How many weeks left in the semester? Not many, right? So let's grind it out. We're gonna learn some buffers. Some of us have had lab already. What do we know about buffers? They suck to make, right? So basically, every time I've ever made a buffer using the formula that we're about to learn, it has never worked. And every single person I ever talk to does it, it also doesn't work. But it gets it pretty close. And then you adjust the pH to your desired pH by adding acid or base in whichever direction you need, okay? Um, I don't know why it doesn't work. I mean, if you're a biologist, you're going to make a lot of buffers in your life. If you're a chemist, you're gonna make much less, but if you're a biochemist, you'll probably make some buffers too. But like I said, I did do my research where we were trying to mimic physiological conditions. Since blood is a buffered system, we would make a buffered buffer to test our quencher and dye that we would test our glucose sensing in. Okay. So to summarize what we talked about on Monday, buffers resist pH change, right? They don't completely cancel out pH change. Adding acid or base is still, acid will still drop the pH, base will still raise the pH, but it's much, much less than what we see if you have an unbuffered system. What makes a buffer? A buffer either contains a weak acid and its conjugate base. How do we know what a weak acid is? It's not a strong acid. Its conjugate base is whatever that acid is after it loses its proton. So choose a weak acid for me, Emily. Any weak acid in the world. Very good. HF. Oops. HF. So does everyone agree that that's a weak acid? Yes. How do we know that? Not on the strong acid list, right? When it deprotonates, it makes H plus and F minus. So F minus is the conjugate base of that weak acid. Everybody see that? And what that means is it is going to, if we put HF and F minus in solution, but can we just put straight F minus into solution, Jack? So how would we, if we were going to go into the lab and we wanted to make a buffer with hydrofluoric acid and some F minus, what would you look for to find F minus? Mix it with sodium plus. So sodium fluoride basically should let us know that it's Na plus and F minus. This is a non-pH inducing ion, so it's not going to affect anything. Therefore, adding NaF would just be adding the F minus that we need in there. And we could do it at the desired molarity and things like that. You could use KF, you could use LIF. All of these three would give the same kind of effect. Theoretically, you might be able to use calcium fluoride because the calcium is non-pH inducing, but then you have to think about the stoichiometry. And sodium is always pretty much the cheapest of all the ions that we're gonna be dealing with. So when we have both of those in there, the weak acid neutralizes any added base, though it does make a little bit of the conjugate base of that acid. So that's why the pH still increases a tiny bit because you're still adding the conjugate base of a weak acid, which in the last homework you saw. And then the conjugate base will neutralize any added acid. That means it protonates to become that weak acid. And we all know that weak acids or decrease the pH of a solution. So all of this stuff leads us to this thing here. That's going to take us to the common ion effect, okay? So the addition of the conjugate base causes the acid to dissociate less, as we'd expect from Le Chatelier's principle. With Le Chatelier's principle on that last exam, I thought that was 5 free points for everyone, but some of us still have to work on that. That's why we do corrections. Basically, we have to think about what's being added. Does it push it to the other side? As long as it's not a solid or liquid, yes. If you're taking away something, it does that. So these things are in play. So the common ion effect just shows us that when we add in the weak acid, we have a pretty low pH because it's generating H plus. When we put in sodium acetate, which is the conjugate base, that is a weak base, and it is going to have a pH that is slightly basic. When we put in equal amounts of both, the pH isn't as low as normal. The conjugate base of that acid causes it to dissociate less. So let's think about this, right? HC2H3O2 makes H3O plus and C2H3O2 minus. So when it's just the weak acid, the H plus concentration is going to be whatever relates to this pH over here. It's pretty acidic, right? When we add in some of this sodium acetate, if we add in C2H3O2 minus, so if we add this, what is going to happen to the equilibrium, Nana? When we add the acetate anion, like we're showing the common ion effect is, if according to Le Chatelier's principle, adding this product is going to do what? What do you think, Cade? It's going to shift to the left. So if we're adding product, it's going to shift to the left, thereby lowering the H3O plus concentration, which means that we have less H plus now, which would mean that the pH is going to go up a little bit. Does that make sense? So this common ion effect is basically causing the thing to dissociate a little bit less because we're automatically adding in product, which means you're going to have less product or less H plus. So if you don't understand that, just believe me on it. Okay. Let's calculate the pH of a buffer solution. Anybody ever do one of these things before? What is this called, Alondra? Ice table. Is that our favorite thing to do in the world this semester? Only if you want to be good at this class, okay? You could like ignore it, but you will have a hard time in this class if you ignore it. Now, if we have the pH of a buffer that is 0.1 molar acetic acid and 0.1 molar sodium acetate, notice how our ice table is the same as usual. We have 0.1 molar acetic acid as our initial, but what is this 0.1 molar acetate anion in there? What is this from, Rebecca? What is this from, Ray? Anybody know? Anybody? Claudia, what do you think? Why am I putting 0.1 molar starting? Remember, every single ice table we've ever made, one side's always pretty much been 0, right? Why am I starting with 0.1 over here? Any thoughts? Jackson? Okay, let me go the other way. Yeah, let's get it smaller for you, okay? So the 0.1 right there, look at what we start with. A buffer contains 0.1 molar acetic acid. 0.1 we put right there. And 0.1 molar in NaC2H3O2. What is NaC2H3O2? What's another way we can think of that? Danny? Whenever we see sodium with anything, what do? Huh? We get rid of it. And sodium is a cation. So we're going to be getting rid of the sodium and losing a positive charge. So if we have Na plus, that means that this thing, when it's neutral, must be, so if it's with that plus, it's C2. So you see that right there? That 0.1 molar is the common ion effect. Have you all ever learned about the common ion effect? Yes, very good. So we should think about the last slide we talked about. Everything we learned in this class is whatever the word means that keeps building on itself. What's the word I'm looking for? Cumulative. Thank you very much, Bailey. So we're gonna set up a nice table. Do we know which direction this is going to shift? What do we think, Janessa? Are we going to add to the products or add to the reactants? I'll give you a little hint. You can look right here to see which side's getting plussed. Ida? The products, right? We're putting pluses here. Why is it the products, Ida? Huh? Because that side has zero. If a side has zero, you can't make something from nothing, right? Except for us in class, we make a lot of something from nothing. We don't show up and we hope we're going to get a good grade in the class. And we just expect to watch the video while we're playing Fortnite or whatever video games we play nowadays. Anybody in here still play Fortnite? Wow. So does my son all the time. So basically, since that side has a zero, we know we have to plus on that side. If it's getting plus to the right side, we also have to plus to that side. We also have to subtract that side. We fill out our ice table. We do minus x plus x. Are we gonna make the x's small approximation? What is the Ka of acetic acid? 1.8 times 10 to the negative 5. Let's go ahead and use it. We solve for x. I'm not going to go over this because we've only done it at least 17 times in this class. We get 1.8 times 10 to the negative 5. We divide that by the original concentration, 0.018%. Is this approximation valid, Carissa? Why? It is. Less than how much? Less than 5%, right? So the approximation is valid. We can then solve for the pH of this solution, which is 4.74. That was what we saw on this other slide. When we had a 0.1 molar mixture of each, it gives us a starting pH of 4.7. Any questions on this? Okay. Oops. Now, let's go on. So, do we like making ice tables? Yes or no? Or let's just not answer and just say, like, no, we don't do anything, right? Do we like doing it, Bronson? Yeah, I don't have a problem with it either. You know why? Because I practice it a lot. Actually, I hate them, honestly. But if I was in this class, I would make them all the time because that's what makes you successful. Yes. Who can answer that question? Anybody know? Did we have something like a table of weak acids that have something called a Ka value? So anytime we need that Ka value, it's going to be on this back page of homework chapter 15. Sometimes we need to solve for the Ka or the Kb. Do we know how to do that one? That's using the formula. So most of the time we can look that up, but there was a problem. So you're going to just look it up. Like if it's a problem, I would give it to you if it's on a test or something like that. Since it's a take-home exam, I'm not going to give it to you. We're actually like kind of far ahead of what I normally am at. So I don't even know why I'm giving you a take-home exam. Should we switch it back to in class just to make everybody, because I heard people saying they're worried that people are going to cheat. Is anybody in here going to cheat? Just kidding. You don't have to lie to me to my face, okay? If I give you a take-home exam, I don't want you to cheat, okay? If I catch you cheating, so if I accidentally make a wrong mistake on the homework and you find out from someone else like, "Oh, this problem the right answer is 4.2, maybe I purposely put in the wrong answer and I go back and manually check it." Do this on your own. You should not be asking anybody else what the answers is, okay? So on this take-home exam, you're going to put your answers into Canvas. If you go and ask someone else who submitted it early, "Oh, what'd you get for this?" and they got it right, or they got it wrong and then they find out the right answer, you're proving to me that you're cheating by talking to someone who already did the test, okay? So that's just me backing up. I did have one error on the last quiz also. I'm sorry about that. I will try and minimize those errors. Do you want me to not give multiple choice and make you just put in the answer? Will that make it easier? Probably, right? Makes it easier, right, Jackson? That way you're not like, well, let me just guess one. Let me actually solve the problem. Yes, please solve the problem. Okay. So this isn't terrible. You should be good at doing this. But has anybody had lab yet this week? Raise your hand if you had lab. What can you tell me about lab? What did you learn? Huh? It sucked? Why? When was it? Yesterday? Okay. I don't think it sucked. Well, I mean, your teacher called me during it, so there were some issues. But those of us who have had lab, we learned that there is this shortcut equation. This shortcut equation is called the Henderson Hasselbach equation. Okay? This is an equation derived from the Ka expression that allows us to calculate the pH of the buffer. Do you want me to show you the derivation? I don't even know it, so I'm not going to show it to you. Okay? But it's got a lot of math involved and it sucks. Nah, I'm just kidding. Derivations are cool. I know people who derive things for fun. Do you ever do homework and like you get the right answer every time and you're like, yes, and you feel good about yourself? Start getting the answer right when you're doing your homework and you'll get that feeling, okay? But in general, when I used to take like classes like math and things like that and chemistry, I hated all the problems, right? But when I was doing it and I was getting it, I actually enjoyed it. I'm like, hell yeah, I got this right. You check in the back of the book, right, and stuff, and you see the answers. It makes you feel good. So I mean, maybe I just like to do problems and stuff like that, but I promise you I don't because I don't do them for fun anymore. But what happens is you can calculate the pH of a buffer system using this equation, okay? It's a big shortcut. Everybody write down this equation you think it's important to use. This equation is making the assumption that the X is small approximation is valid, okay? If the X is small approximation is not valid, you have to do the ICE table and you can't make that X is small approximation. In a real world of what I'm going to give you, I don't expect you to have to do the hardcore one. I just expect you to be able to do this one. So in this equation, if you wanted to make a pH buffer with a pH of, what was your buffer, Bryce? What is the one that you get assigned to you? So what you would do is you can say, like, if I want to make a buffer that has a pH of 5.7, you have to decide which acid to use, right? Because all of the acids have different pKa's. Did he talk to you about that? Which one to decide to use? Yeah. So basically, let's take a step back, okay? You want to use a acid base combo, a weak acid and its conjugate base combo that has a pKa that's closest to the pH that you're doing because it'll keep this ratio the closest. You could do a buffer that has a pretty far pH from the pKa, but you're going to have like way more of one than the other. And now that buffer is not going to be as effective because it can only, if you have equal amounts of both things, now you can resist changes to both acid and base because you have equal amounts of each, right? So let's just say we split the class in half. Half of us are the acids, half of us are the weak base, right? Every time someone comes in, if it's an acid, the weak base would go and neutralize them, right? If we have 50 weak acids and 50 weak bases, we could theoretically neutralize 50 either acids or bases that come in, right? If we had to use a ratio like 90 to 10, we would still have a buffered system, right? But now we could resist 90 of whatever we have the 90 of, but we can only resist 10 of the other thing. So in general, an ideal buffer has closer to equal volume or concentrations of the acid and the base because now it's an effective buffer in neutralizing both of those things, okay? Now, there are situations where if you know only acid's going to come in, maybe you would want a buffer that has more base because that's the thing that has to react every time coming in. But in general, we want buffers that can resist pH changes in both directions, okay? So let's go ahead and do this. So let's calculate the pH of a buffer that contains 0.25 molar benzoic acid and 0.15 molar sodium benzoate. Given that the Ka is 6.5 times 10 to the negative fifth, so this would be that value, right, Nana, that you were talking about. Like you could look this up in the list of weak acids. So The equation we're going to use for this is pH equals pKa plus the log of concentration. And look over here. This is in, what does this bracket mean? Concentration. So we can plug in the actual concentrations. I know the concentration is not written over here, but that's just because we're being lazy. I would say I wrote this, but that's way too nice to be my handwriting, so you know that's not it. So what we're going to do is we're going to plug it. So we want to solve for the pH. Do we know the concentration of the benzoic acid? The acid's going to go on the bottom, so it's going to be plus the log of 0.15 over 0.25. Okay, that is this part of the equation, but we need the pKa. They only gave us the Ka. How do we calculate the pKa of this? What do you think? The negative log of the Ka, which is the negative log of 6.5 times 10 to the negative fifth. Everybody punch this in your calculator and prove to me you know how to do this. Like I said, following me and seeing the answer is one thing. Get it so your calculator shows it. Everybody's calculator is different, and it doesn't always work out the best, right? What do we get? How much? 4.19. Okay. So now we can say the pH is equal to 4.19 plus the log of, so what I would do is I would do 0.15 divided by 0.25. What does that equal? Should be less than 1. How much? And then push log now of 0.6 or log of second answer. What'd you get, Ray? Negative 0.22. Before we solve this, okay, do we have more acid or more base in this mixture? What do you think, Zeus? What do we have more of, acid or base? Based on the numbers in front of the acid and the numbers in front of the base, its conjugate base. Which has a bigger number? 0.25 or 0.15? What's bigger? So, and the 0.25 is the acid. Everyone agree with that? So we have a little bit more acid than base. So doesn't it make sense that this is the value if you had exactly equal amounts? We're subtracting some. When we have a little bit more acid, should that reduce the pH a little bit? What do we think in that case, Emerson? Does extra acid, drop the pH or raise the pH? So does a negative make sense? Yes, it does, right? So the pH of this solution should then be, so 4.19 minus 0.22, which gives us 3.97. Notice how I originally had that wrong. I'm just showing you. And once again, that's not my nice handwriting, so I didn't make that mistake. I don't know who I borrowed it from, but that is the case here, okay? Let's go ahead so everyone understand. So we could do this same thing using the ice table, but I think we're kind of tired of ice tables. So let's see, what if it was 0.15 benzoic acid, HA, and 0.25 of A minus. So let's do the same thing. pH equals 4.19 plus the log, but now we're going to flip 0.25 over 0.15. So what is 0.25 divided by 0.15? What does that equal? And what does the log of 1.6 equal? So this would be plus 0.22. Now that we have more base than acid, does it make sense that the pH should be a little bit higher than the straight up? Yes? No? Okay. Let's try and calculate the pH of this buffer solution. Okay. Let's calculate the pH of this buffer solution using the Henderson Hasselbach equation. pH equals pKa plus the log of base over acid. And what was that value that you were asking about, Nana? The Ka value? What was the Ka value for this one? You have it in your notes? It's like 1.5 times 10 to the negative 5 or something. 1.8 times 10 to the negative 5. So we can calculate the pKa from the Ka, right? Valerie, did you do that in your calculator? So you're just gonna assume like, yep, my calculator knows how to do that, and I'm good at that. Avery, where's your calculator? What's the log of 1.8 times 10 to the negative 5? Well, but it's negative log of that, so it's positive 4.7. Okay. And what is the concentration of B in this case? What should it be? 0.1. And what is the concentration of acid in this case? Also 0.1. What is 0.1 divided by 0.1? What is the log of 1? The log of 1 is 0. So remember how I said when we have a little bit more base than acid, it raises the pH? When we have a little bit more acid than base, it drops the pH. When we have equal acid and base, they cancel. Therefore, the pH equals the pKa. So here, listen to this. pH equals pKa when concentration of HA is equal to concentration of A minus. Okay? So when we did this problem using the ice table, what did we get? 4.74. What did we get using the Henderson Hasselbach equation? 4.7. Maybe there's a 4. Maybe we lost it in sig figs, right? But does it show us that it solves for the pH the same way? So if given the option, do we want to use the Henderson Hasselbach equation? Only if you want to save time and money. You know why you save money? Less ink. And if you're using a tablet, less electricity. Okay? So that's how we do that. Let's go ahead and calculate the pH of this buffer solution. You have 2 minutes. If no one tells me the answer by 11:30, the third exam will be in person. And that's a lie. It's not going to be. But I just want to give you some pressure. Anybody solve for it yet? pH equals pKa plus log of base over acid. Base concentration is how much? Over 1 plus, so we have to do the negative log of 6.6 times 10 to the negative 4, right? What'd you get for the pKa, Analia? Everybody else get that? 3.18 is the pKa. Is these equal? So they're going to have a value, right? And there's more acid than base, so it should theoretically be a negative value. What'd you get for log of 0.5 over 1, Bronson? Negative 0.3. 3.18 minus or plus negative 0.3 gives us 2.88. 2.88, maybe. So we got 3.18 as the pKa. We plug that in. 2.88. Everybody see how we do this? Pretty easy. Why was lab so hard on Monday? I'm just kidding. why was lab hard about it, right? So in lab, we give you a pH to calculate. You have to decide. So let's continue on with the lecture. Okay. So there's a whole bunch of these you can do for practice. We're not going to do it. Oh, here's how we derive the Henderson Hasselbach equation. Skip. You can watch this on your own if you want. Okay. Look at that. Oh, we negative log each side and we blah, 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 blah. We're not doing that. Henderson Hasselbach versus equilibrium concentrations. We've already showed that for the 0.1 one. We get the same answer for both, so we're going to skip that. Do I use the full equilibrium analysis or the Henderson Hasselbach equation? The answer is the Henderson Hasselbach is generally good, except for when the x is small, approximation is not valid. So how can you decide? Generally, the x is small approximation will work when both of the following are true. The initial concentrations of acid and the salt are not very dilute, and the Ka is fairly small. So if you're using a very strong weak acid, maybe it won't work because it's going to dissociate a lot, right? So I would just always use it. And if you get it wrong, it's only a couple points off. But actually, it's a take home. So you should do it both ways every single time, just so you learn this and become experts at it. So for most problems, this means that the initial acid and salt concentration should be over 100 to 1,000 times larger than the value of the Ka. Okay? So that is kind of the thing. So if you're like got a Ka of 1.5 times 10 to the negative 2, and you're starting off with 0.1 molar, that's like 0.1 to 0.01. That is not 1,000 times bigger, right? But if you start off with 0.1 molar and the Ka is like 10 to the negative 5, that's like 0.00001. That is 1,000 times more. And we saw that it worked when we were doing with the acetic acid one. Okay. So real quickly, a conceptual question. A buffer contains weak acid Ha and its conjugate base A minus. The weak acid has a pKa of 4.82 and the buffer has a pH of 4.25. Which statement must be true of the relative concentrations of the weak acid and conjugate base? So this question is saying we make a buffer with a pH of 4.25, right? That buffer has a pKa of 4.82. Do we have more acid than base? Do we have more base than acid, or do we have roughly equal? What would the pH be if they were roughly equal, Kayla? If we had equal amounts of acid and base, what is the pH equal to? Any thoughts? It's the it's it, so when they're equal, log of 1 equals 0. So when they're equal, pH is equal to pKa. Okay? So is the pH equal to the pKa? No, it's not. We can eliminate that one. So Sydney, the pH, is it higher or lower than the pKa? Is less. So does that mean we probably have more acid that brings it down lower, or do we have more base that brings it down lower? Base actually increases the pH. So more acid means that, so what we should say is there should be more acid. So since the pH of the buffer is less than the pH of the buffer must contain more acid than base. Everybody see how this works? So if we understand when they're equal, pH equals pKa, we can then kind of figure out whether or not we have more acid or more base, because we know acid drops pH, base increases pH. Everybody comfortable with that? Ish? Okay. So how much does the pH of a buffer change when acid or base is added? So now we get to learn a fun new technique, okay? This is called calculating the new pH after acid or base requires breaking the problem into two parts. First part is a stoichiometry calculation. Have we ever done that before in our lives? Only if you pass 115A, which means that you all should have done that, so you all have. Or maybe you skipped that part, right? And you just did good on everything else. So a stoichiometry calculation for the reaction of the added chemical with one of the ingredients of the buffer to reduce its initial concentration and increase the concentration of the other. What that means is if we add acid, it reacts with the A minus to reduce the A minus, but it also increases the HA. Does that make sense, right? So as far as the analogy goes, right? If half of us are buffers wearing hats and half of us are buffers not wearing hats, right? and now a new person comes in without a hat. How do we keep that from changing the pH? One of the people with hats takes off their hat and gives it to the person who came in, right? So if we had 50 and 50, right, equal amounts of each, 50 hats, 50 no hats, somebody comes in, they take the hat. Now all of a sudden, there's another person with a hat, or no, there's so that we don't count that one that comes in. I don't know. The hat one doesn't work all the time. Okay. Um, if base comes in, so when there's A minus, right? So if we add acid and let's just say we have three A minuses and three HAs, would this be a buffered system right here, the circled part? Does it have the weak acid and its conjugate base? Yes, it does, right? So now when we add acid, what's going to happen to the acid, Bronson? That one of these A minuses is going to go and grab that H plus. So now all of a sudden we go from 3 to we lose one. We now have two A minuses left, but this A minus grabbed the H plus to gain another HA. So now we have two A minuses and four HAs. Everybody see that? We lost one here, but we gained one over here. That's what they mean by a stoichiometry problem in thinking about what happens. And now that we do that, now we just do our normal equilibrium ice table and or what's the other thing we can use, Ricardo? That's not the ice table. Starts with a Henderson Hasselbach and ends with a equation. The answer is Henderson Hasselbach equation. Very good. Okay, so let's do a buffer problem. Okay, so realistically, like we're doing a lot of these little things. Most of the exam is going to be a titration problem. Okay, because that covers all of the concepts we've been learning. It's like one problem to rule them all. Okay, what's that from? Oh, nobody got extra credit. Too late. What'd you say? Very good. Remind me, I'll give you extra credit. We demonstrate this calculation with a 1 liter buffer solution that is in the generic acid HA and its conjugate base A minus. Since the concentration of the weak acid and the conjugate base are equal, I don't even know where the problem is. The pH of the buffer is equal to the pK. Let's calculate. So where's the problem? Okay, here's the problem. So in this problem, what the hell is the problem? All right, let's make up this problem, okay? So in this problem, what we are saying is we have, what is it, dude? It's a hard one. The problem. So, I mean, that's telling us how to do it, but where's the problem at? Okay, so in this problem, let's see. We are starting off with 0.1 molar of each, I believe. Okay, so we're starting with a 0.1 molar HA and 0.1 molar NaA. What can we consider NaA to be? Amanda, when we see NaA, what do we think of that as? Cade? No problem. Mine isn't either. That's why I'm making all these mistakes. Cade, when we see NaA, what does that mean? Nope. Abby? We take away the Na plus, so what does that mean it is? Take away an Na plus from NaA. A minus, very good. So do we have our weak acid HA and our conjugate base A minus? Yes, we do. Okay. So in this problem, what we're talking about is we have equal moles of A minus and HA. Everybody see that? Because it's a 1 liter buffer solution. So if it's 0.1 molar, that means there's 0.1 moles of each of these things. Everyone comfortable with that? Now the question's saying, what happens to the pH after 0.025 moles of strong acid is added. Okay? So if we start off with 0.1 moles of A minus and 0.1 moles of HA, and now we add in 0.025 moles of strong acid, what is going to get reacted? Robert. So we're adding into this reaction 0.25 moles of H plus, right? Because we're adding strong acid. The A minus reacts with the H plus to form HA. Does everybody see that? So when we started off with zero point 0.1 moles of each of these things, of A minus and HA, when we add 0.025 moles of this, I like to think of it as we subtract 0.025 moles over here, and we add 0.025 moles over here. So the book doesn't write that in. When I learned it in high school, I guess. So you know what was weird is I never took this class in college, and it's probably the biggest mistake of my life because I got AP credit. Like AP credit, you're like, oh, it's so cool. Well, I was a chem major and I had no base of gen chem, and I didn't learn this until after I graduated grad school. So you think my teacher in Hawaii actually taught this? Probably not, right? All we were doing was like hanging out in the sun and eating coconuts all the time. This is before internet and stuff like that. You know, that was a thing. That's what people used to ask me in college when I started. Like, do you guys have telephones over there? I was like, no, what are those? Um, Weird, huh? Now there's internet. Now we know. So the A minus, why is it minus 0.025, Meredith? Why am I putting this minus 0.025 right here? Because the A minus grabs the H plus that comes in. So that's no longer A minus. We lose it. So it goes down to 0.075 moles, right? But those 0.025 H pluses that came in and grabbed the A minus is making 0.025 more moles of HA. So when you take the 0.1 that was there originally plus the 0.025 that got added, now we have 0.0125 moles of HA. So that is the stoichiometry part of the problem. How can we solve for the pH of this? Merve. Very good. We can use the Hasselbach equation if we want to just not give any respect to Henderson, Harry and the Hendersons, right? We only like Hasselbach. I'm just kidding. I don't really think you need to ever refer to it by people by name because it's usually a boss who kept down their young grad students who did all the work and stuff and didn't give them any respect and things like that. Anybody ever hear of that situation? That's what happens in real life in science. But you know what? They're the ones who get all the money and they're the ones who pay you. So you should just be happy. They give you a PhD and then you go make your own name equation. So how do you do it, Merve? So one thing that's missing from this problem is what? Nana? I'm asking you because you asked that question earlier. Yeah, so we don't know the pKa because we don't know what acid it is. So this is saying you can make an ice table. So the Ka that they were using, oh, so they're just showing you it in terms of Ka. So it would be the ratio times Ka. I think that's weird. We would just do this problem. So if whatever the acid was, we'd look up the Ka and we could find the pK of it. Okay. What happens when base is added to a buffer, Alondra? What's the difference? So we're starting off with the 0.1 molar of each of these things again in our buffer system, right? Now we're adding base. What's going to happen? Is it the same or is it different? What's different about it? Tiana, what's different? So the last one, I showed you what happens when we add acid. Now I'm going to show you which is base. So let's say we're doing this for acetic acid and C2H3O2 minus. Let's actually solve for it in this time. So we have 0.1 molar of each of these things in solution. We're adding 0.25 moles of sodium hydroxide and we're assuming that the volume doesn't change. That assumption is because if the volume changes, it would dilute everything. We're going to assume that the small amounts of pellets that we're adding doesn't change it. So what do? What's different, Kiana? Riley? Why not? Why not? Valerie? Donatella? Did anybody know? Thank you, Kayla. Say it again. The OH minus is not going to react with A minus. Minuses don't react with minuses. The OH minus reacts with the HA. The HA donates its proton to the OH minus. That makes water. Does water affect our equilibrium? No. But the HA lost its H, so it became A minus. So we say we lose 0.025 moles of the HA and we gain 0.025 moles of the A minus. And now we have the thing with our ratio. What was the pKa of acetic acid? Was that the 3.91 or what was it? It was over here. What was it, Robert? Was it 3.18? No, that's hydrofluoric acid. 4.74. Thank you. This looks like the right one. So the pKa is 4.74. So if we want to find the pH of this solution after addition, it would be pH equals 4.74 plus the log of what goes on the top, Bryce? What number is that? So in this case, we do 0.125 over 0.075. One problem with this. What's the problem, Avery? This is the number of moles and not the concentration. Any fix to that, Loit? No. If you have this like 0.125 in relation to 0.075 and you're in the same solution, does it matter if we're in moles or we're in concentration? Is the ratio going to be the same? The ratio remains the same. So in this case, it doesn't matter that we're using moles because the ratio of the molarities should be the same since they're all in the same solution. Okay? So what does the pH change to? Log of 0.125 over 0.075. Anybody? Anybody? Does it make sense that the pH is higher than what was the initial pH before addition? Very good, Bronson. How do you know that? The concentrations were equal, so the pKa. When we had a 0.1 molar of each thing, that means log of 1 equals 0. The pH was originally 4.74. When we add base, does it make sense that the pH goes up a little bit to 4.96? 4.74 originally, add NaOH. Is that a large change? What if we just had water and we added 0.025 moles of OH minus? What would be the pH of that solution? What's the negative log of 0.025? 1.6, which is the POH. That means we do 14 minus this. That means the pH of this is 12.4. So if we use pure water, the pH from 0.025 moles of base added goes from 7 to 12.4. That's a change of 5.4. Is that significant? Yes. When we add it to a buffered system that starts at 4.74, it raises to 4.96, 0.26. Are we seeing the effect of having a buffer? Yes? All right. Go get buff and tough with your Afro puffs. I got an Afro puff, so. All right. Aloha. Those of you in my lab, be ready to crank it out today because that group said it sucks, but they're not in our lab. Our lab is always awesome. Aloha.